All right. Final question for the AP Calculus BC 2024 free response questions. And as expected, we see a question here with a Maclaurin series. And so we're given a Maclaurin series, which is just a Taylor series that is centered at zero for some function, and it's defined here in the summation notation. And we're told that it converges to f of x for all x in this interval of convergence. Okay. It can be shown that this Maclaurin series for f has a radius of convergence of 6. So I'm actually going to go ahead and underline that part here. That's going to come into play a little bit later. Now, part A. Now, determine whether the Maclaurin series that is given for f converges or diverges at the value x is equal to 6, and give a reason for our answer. So we're going to start by actually plugging in x is equal to 6. So when x is equal to 6, what happens? So let's look at our series. So n is equal to 1, infinity, n plus 1, and we're raising 6 to the n power, all over n squared, 6 to the n. So we can see here that these 6 to the n terms are going to divide out. And so what you're left with is the following series in its more simplified form. This is just n plus 1, and I actually don't need parentheses, n plus 1 over n squared. Now, if you really want to, you could write this also as this series where we're just dividing everything by the denominator. So that's 1 over n plus 1 over n squared. Maybe we want to put parentheses around that. In any sense, we have that following series. So the question then is asking, what is going on here? Is this series going to converge or diverge? Meaning, will it have a finite sum, or will this sum continue to grow without bound? Well, think back to your convergence tests, and we should see here that we should be able to compare this series, and I'm just going to copy and paste this here. I'm going to be able to compare this series to, and actually, you know what? Let me actually compare it to this. Let me take it in this form. So I'm going to take this series. Oh no, I don't need all this. Well, I'll just write it. We can say that this series here, n is equal to 1, 1 over n plus 1 over n squared, can be compared to the following series. And you could have done this without sigma notation if you just want to look at the general terms, right? But we can compare this to 1 over n. So I guess what I'm saying here is I can go ahead and erase these sigmas and just compare these two series here and say that this is greater than this. But if you want to keep the sigma notations, that's fine. So I'll just put them in there. But what do we know about this series? So we can compare it to 1 over n, right? And what we see here is this series on this left side is always going to be greater than this series 1 over n. So I'm going to write that. It's always greater than this series 1 over n. For any n value, the values or the terms in this series is always going to be greater than the terms in this series. Now, why is that important? Because this series, if you notice here, is a harmonic series. And you can watch my videos on a harmonic series if you just go back. But we can see that because this series is a harmonic series, which diverges. So this series here diverges because it is a harmonic series, okay? And what can we do when we're doing this direct comparison? We can say, since this series is greater than this series, and maybe I want to kind of qualify that for all n is greater than 0, okay? We can then say, therefore, this series here that we're working with, when x is equal to 6, 1 over n plus 1 over n squared, this series is going to also diverge by the direct comparison test. By the direct comparison test. And that is the name of the test that allows us to compare one series to another series and say, since this series is always going to be greater than this series over here, and this series is growing without bound, meaning it will never be able to have a finite value for its sum, therefore this series must also diverge. If the smaller series diverges, then the larger series also must diverge because it's always going to be greater than that, okay? All right, so there is part A. Part B, it now is saying that it can be shown that this series, given here, f of negative 3, plugged in here, which is simplified into this form right here, and that the first three terms of this series, s sub 3 is equal to negative 125 over 144. We want to show that f of negative 3 minus s sub 3 is less than 150. So what we're dealing with here is a partial sum. And it's saying, hey, how good of an approximation is this partial sum to the actual sum, or the actual sum of this infinite series here. And can we show that how much we are off by, right, or our error, if you will, is less than 150? All right, so a couple things that we probably should do here. I'm not sure if the scoring guide is going to require this, but the first thing I do want to do is I just want to show that this series, n plus 1 over n squared times negative 1/2 to the n, because this series is alternating, meaning the terms alternate in sign, I want to show that it actually will converge by the alternating series test. So I'm going to say that a sub n plus 1 is less than a sub n. That's the first condition for the alternating series test. That is to say, n plus 2 over n plus 1 squared is less than n over n squared. I'm just looking at a sub n without the alternator, if you will. That's true. And that the limit of a sub n, or the absolute value of a sub n, or just a sub n, this is going to be equal to 0, meaning the terms in the sequence actually converge to 0. So because this is true, this series therefore series alternates, or excuse me, converges by the alternating series test. Alternating series test. Okay, so we've established that this series is indeed going to have sum. So now we can use the alternating series error, right? So the alternating series error, I'm just going to abbreviate for short for this. We're going to show the following. Now the absolute value of f of negative 3, meaning the actual value of this series when I plug in negative 3, the difference between that and our partial sum, which is just an approximation, has got to be less than the absolute value of a sub 4. Okay, the absolute meaning the next term in the series. Well, what is that next term in the series? Well, the next term in the series is going to be, if we're just plugging in 4 into our series, we get 4 plus 1 over 4 squared times negative 1/2 to the n power, so 4th power. And from here, we're just going to do a little bit of cleaning up. 5 times 16. This is just 1 over positive 16. I'm just taking the absolute value of all that, which is just going to be 5 over 16 squared, if you will, which is the same thing as 5 over 256. If I wanted to clean that up even further, I can show that this is indeed less than, well, our goal is to try to show that it's less than 150. That's what our end goal was. Oops, 150, not 115. 150. Well, 5 over 256, that's definitely less than 2 over 250, which is equivalent to 150. So what I've just shown is that our 4th term in our series is less than 2 over 250, which is equivalent to 1 over 150. Therefore, I've just shown that the first 3 terms of the series, or the difference between the first 3 terms in the series and the actual value of negative 3 is indeed less than 150. Okay? All right, now part C. So part C then, we're going back to using the function f, and it's saying the general term for, it wants us to find the general term for f prime, or the derivative of this series, and then find the radius of convergence for the Maclaurin series that we find with our derivative. All right, so first things first, what does this series look like? So f of x, if we start writing out the terms in the series, we would get 2x over 6, and so I'm just plugging in values here, right? We get 2x over 6 plus 3x squared over 4 times 6 squared plus 4x cubed over 9 times 6 cubed, and this is just going to keep on going. And this is just going to go all the way to, again, our general term, which is what's given here, so n squared times 6 to the n plus, okay? Now, our next step is going to find f prime of x, which is the derivative of this series, f prime of x. Well, we're just going to go through and we're just going to differentiate every single one of these terms. So 2x over 6 is just 2/6 plus 2 times 3 over 4 times 6 squared x plus 3 times x squared over times 6 to the third, and I'm just doing a little bit of simplifying right now. Okay, or if you want to, you could just write this 3 times 4x squared, 4x squared over, sorry, I should write that, 3 times 4 over 9 times 6 to the third times x squared plus, and this is just going to keep on going. Really, the fourth term does not really matter. Actually, how many terms do they want? Find the general term. Yeah, it really doesn't matter. So we can just go all the way down to now the general term, which is now, again, I'm pulling the power rule. N times n plus 1 times x to the n minus 1 all over n squared 6 to the n. And I'm pretty sure I did all of the previous terms, right? Okay, yeah, that looks good to me. So there's our derivative. So we can actually just write this in summation notation as the following. 1 infinity n plus 1 times n times x to the n minus 1, all of that times over n squared times 6 to the n. All right. Now, it then asks us to find the radius of convergence. So let me see if I can actually make this smaller without messing everything up. Can I do that? All right, so hopefully you took a screenshot of that. All right, so now we're moving on to the radius of convergence. So for the radius of convergence, it's somewhat apparent to some of you just by looking at our general term that this radius of convergence is just going to be the same as our original series. But when in doubt, we can go ahead and we can just employ the ratio test, right? So using the ratio test, we can say the limit as n approaches infinity of n plus 2 times n plus 1 times x to the n. And you know what? I actually don't think I'm going to have enough space over here. So I'm going to move this over here. And for the sake of this, I'm actually going to make this a lot smaller, just so I have some space to work with. There we go. I'm going to move that over there. You can always move that up. All right, so the radius of convergence. So we got the following. All right, now I think I have some space to work with. All right, so where was I? X to the n over n plus 1 squared times 6 to the n plus 1 times n squared 6 to the n times n plus 1 times x to the n minus 1. And all I'm doing right now is just comparing the next term to the previous term, right, or the current term, if you will. And I'm checking to see, is this ratio between terms, is that limit of that ratio between terms going to be less than 1? That means the terms are getting smaller in such a way that this series will indeed converge. And then we use that to kind of figure out, all right, so for what values is this statement going to be true? For what x values, if you will. So I'm just doing some basic algebra here and just cleaning this up. And then you can do some simplifying. Obviously, this n goes into this n squared and so on. And we can clean this up all the way until we get to, we can clean this up all the way until we get all the way to absolute value of x over 6. Remember, we can factor that outside because it's really not affected by us taking the limit as n approaches infinity. So we have n squared plus 2n all over n plus 1 squared. Well, what's the limit of all of this as n approaches infinity? Well, that's just going to be 1, right? The highest degree in the numerator and the denominator are the same. The leading coefficient is 1. So we really just have the absolute value of x over 6, which is less than 1. And then from this, you can write the following inequality. So therefore, the radius of convergence is 6. Oops, and this should be 6 here, not 1, sorry. All right, so now the radius of convergence is 6. So for any values between -6 and +6, you can see there, this series will converge, okay? All right, now let's look at part D. Part D, I'm going to move this up now since we have all the space we need. So then for part D, now consider this function g of x and use the ratio test to determine the radius of convergence of the Maclaurin series. So this is the fact that they specifically stated the ratio test leads me to believe that we may not have needed to actually do the ratio test for the previous one, but you know, it's better to be safe than sorry. So part D. So let's apply the ratio test again. So we're doing the ratio test now for this new series, ratio test. So we're going to write this out and bear with me. And first, all I'm doing right now is I'm just evaluating my general term at n plus 1. And then I'm going to divide it by my general term evaluated at n, or just as it is. And the limit of this as n approaches infinity is x to the x squared times n plus 2 n squared over 3 times n plus 1 cubed. And continuing on here, we can see again the limit for x squared over 3, the limit as n approaches infinity of n plus 2 n squared n plus 1 third is 1. And again, same kind of deal as the previous problem. We know that the highest degree n term in both the numerator and denominator is 3, and therefore the leading coefficients when we compare that is just 1. So all of this just cleans up really nicely to just absolute value of x squared over 3 is less than 1, which we can write as the absolute value of x squared is less than 3. And just from this, you didn't really have to show any algebraic work. We can just say, therefore, the radius of convergence is root 3, or the square root of 3. All right, so that concludes all the FRQs for the 2024 AP Calc BC exam.